Hello, everyone, and welcome to another webinar from Optiwave. Today's webinar would be on what's new in OptiSystem 21 new release. Okay. So the webinar outline, let me just put the web pointer on. I'm going to give some overview about Optiwave quickly, and then I'm going to show the product line of Optiwave and showcase the new components and visualizers being added to OptiSystem 21. And then I'm going to discuss the new improvements, and we show demonstration for some applications in quantum key distribution, sensors, underwater wireless communication, and single photon detector. Okay. So Optiwave is established in 1994. It's located in Ottawa, Ontario. And Optiwave, as you know, it developed software tools for designing, simulating, and optimizing components, links, systems, and networks. Optiwave software offers users a competitive advantage through the shortening of product time introduction to the market because of using simulation ahead of producing the product, improving the product quality through the investigation of many effects which you could not do that with the actual devices, as well as you can enhance the productivity and cost effectiveness. Optiwave products, the different packages of software has been licensed in over than 1,000 industry corporations, universities, research and governmental institutions in over than 80 countries over the world. The product of Optiwave is categorized into 3 levels. One of the system level, where we have OptiSystem software. Today would be, the webinar is about the release 21. And there is OptiSpice software, which is an optoelectronic software used to design different optoelectronic circuits, including photonic integrated circuits. The other package is the component level, where we have, as you can see here, different software packages from beam propagation method, finite difference time domain method, mode solvers, grating, and fiber designs. And then the last package is the instrumentation level software, which is a new software we introduced a few years ago to allow users to set up equipment remotely or physically located with the software and control the operation, collect data, and process the data. We have few webinars on our website you can see on OptiInstrument usage. Now, users can download free trials of any of the software packages from Optiwave website. So if you go to website there and then you go to the download link here, you can go double click on the 30 days free evaluation. Then you will pop up this page where you need to register. You need to use your corporate or university email address. And then after you create accounts, you will be able to download the software packages, and these software packages will be going to the program files, C drive program files, and then Optiwave software. As you can see here in this slide, you can go to the C drive program files, Optiwave software, and the different software packages can be downloaded on that page. And then if you click on one of these directories, you're going to see the subdirectories where you have the documentation of that software, as well as the drivers and other instructions and software. In this part here, I'm going to talk quickly about the different components we support in OptiSystem software. So we have over 580 components, which include sources like light sources like CW lasers, LEDs, VCSELs, DFB lasers, Fabry Bureau, white light sources. We support also different modulators types like Mach-Zehnder modulators from single drive or dual drive, as well as electro-absorption modulators, phase modulators, AM modulators, FM modulators, bit sequences. So we offer random sequence generators, which can be generated randomly, or users can put their own sequences in the components. As well, we have compliance test patterns can be used for testing setups like and in terms of jitters and other parameters. In terms of fibers, we have single mode fibers, multi-mode fibers, and multi-core fiber components where you can model your designs using these fibers. In terms of modulators, we have optical modulators, as I mentioned above here, and electrical modulators where you can do optical orthogonal frequency division multiplexing or quadrature modulators. In terms of modulation formats, you could do all types of modulation formats, including return to zero, non-return to zero, carrier suppressed return to zero, dual binary, differential phase shift keying, any type of MPSK or QAM, pulse amplitude modulation, pulse position modulation, probabilistic amplitude shaping. So all of that is available in OptiSystem. And we offer also filters, optical filters, electrical filters, and filters using FPG as well, fiber Bragg rating filters. In terms of optoelectronic circuits, we offer through OptiSpice ring resonators because OptiSpice works cohesively with OptiSystem, so you can design resonators or create laser drivers and then use them within OptiSystem. Switches, there is different types of switches, electrical switches, optical switches, and so on, and optical interconnect. In terms of signal processing, there is DSP, digital signal processing, with a very sophisticated algorithms to do different equalizations and adaptive filtering. There is other equalizers, electronics, and maximum likelihood sequence equalizers. If digital equalizers, Viterbi, phase recovery, data recovery, clock recovery, 3R regenerators components. In terms of forward error correction, we offer Reed-Solomon low density parity check, and there is different types of bit mapping which you can use for reshaping or for coding, 4 bits to 5 bits, 8 bits to 10 bits, and 4-bit to 3T algorithm. In terms of detectors, we have detectors, ABD detectors, and we added up in version 21. We're going to talk about it today, is the single photon detector devices. In terms of amplifiers, we offer a huge library for doped materials, including most available doped materials from erbium, ytterbium, thorium, praseodymium, holmium, as well as semiconductor amplifiers. So we have different models for semiconductor amplifiers, Raman amplifiers. We offer waveguide amplifiers, as well as we offer optimization for any parameters in the software. So you can do optimization, single parameter or multi-parameters or Monte Carlo, as well as gain flattening optimization. Electrical amplifiers, we offer transimpedance amplifiers, limiting amplifiers, automatic gain control amplifiers. In terms of passive modules, you can think about any passive components available in the field. You would have a component representing that. So you have couplers, muxes, demuxes, arrayed waveguides, switches, attenuators, circulators, polarization controllers, and so on. In multi-mode applications, we offer multi-mode fiber, as well as multi-mode amplifiers and doped materials, mode generators, and passive, multi-mode passive components, as well as spatial visualizers to view the modes. In terms of channel, we have the fiber channel as we show. Then you have component to represents the Li-Fi channels, satellite channels, free space optic channel, and visible light communication channel, as well as we're going to talk about today, adding up 2 components for underwater free space communication. In terms of visualizers or equipments in OptiSystem, we have equipments which does view signals in the optical domain or electrical domain, binary or M-ary levels. As well, we have analyzers for bit error rate, eye diagram analyzers, and so on, and plus equipments from the field like light wave analyzers and so on. Most of the components in OptiSystem support either unidirectional or bidirectional, so you can do transmission from west to east or east to west. As well, we have support single polarization or dual polarization in the system. One Excellent resource for we offer in OptiSystem is the example library. And the example library, we have over than 1,000 examples categorized in different categories, as you can see here. And these they cover different applications from advanced modulation, which there's examples on the QAM, on the BAM, on the PSKs, on pulse amplitude shaping. There is examples addressing new radio fronthaul for 5G applications. Or 6G even. Optical amplifiers, there's examples on optimization. So if you go to optical amplifier libraries, there's a huge library there with examples on different types of amplifiers. We support microwave photonics, we support sensors, examples on Phi OTDR, on OTDR, on FBGs, using FBGs, as well as tilted grating, which we added up in version 21. There is some examples how to use other software, which is like OptiMode, to design photonic crystal fibers and then use this photonic crystal fiber for sensing in collaboration with OptiSystem. There is examples on wireless communication for Li-Fi, visible light communication, satellite communication, and new examples for underwater communication. And then spatial division multiplexing, we have few modes, multi-mode or single mode or multi-mode, multi-core fiber example. Okay, and then we have added up examples on quantum key distribution, which is it's something which many users are right now seeking in the field. OptiSystem network, OptiSystem software can work with the other packages of Optiwave products, like we can work with OptiGrating. So what you can do, you can design your software with let's say OptiGrating here, and create the emission and transmission spectra, and then load this into this component in OptiSystem, and then use them in OptiSystem project. The same thing you can do in OptiSpice. These two components, like one of them is netless and the other one is a regular component, where you can have a design in OptiSpice, then feed this design into OptiSystem. And there is a few examples in example library about this behavior or this action between OptiSpice and OptiSystem. Same thing for OptiBPM. There is some examples on MMIs, multi-mode interference couplers, and using this one, as well as there's examples on using OptiInstrument with OptiSystem. Now, also OptiSystem software can work with other software packages, external software packages like MATLAB, Python, C++, Scilab. So with these packages here, you can do either you can call OptiSystem from the MATLAB components. You have your code in MATLAB, and then you would be able to call OptiSystem and then do the calculation, or you can have the MATLAB component in OptiSystem, and then you have a specific functionality of this component and use it within OptiSystem software. So you can have either way. Either you can call OptiSystem from of these software packages, or call these software packages from OptiSystem. However, you need to have these packages like MATLAB or Python on your computer. Okay, now just to summarize here, we have, as I mentioned, over 580 components in the different optical, electrical, binary, and memory regimes. And we have over 1,000 examples in the demonstrating the different applications. Okay, now we're going to move into the second part of this presentation. Is about the new components added into version OptiSystem 21. Now, this is a list of these components. The first component here is called serial to parallel converter. And this component, basically, you can have a sequence of bits here, and this sequence, you can split them into these two ports. And this split can be in a single bit or a multiple bits. You can, for example, take the first bit here and put it here, and second bit, put it here, or you can get 2 bits or 3 bits from the sequence and put them on these bits. And you can have multi ports here, okay? The other component is a digital comparator, where you can compare this sequence on this port or sequence of bits on this port, and then you can compare bit by bit or group of bits with a group of bits. And then the outcome here would be if you have a match or no match. The other two components here, as you can see, this is under addressing the underwater channel. So we have one called line of sight, where the signal from the transmitter telescope going directly into the receiver telescope, and the other component called non-line of sight underwater component, which is the received signal here is going not directly through from the transmitter scope, is actually reflected from the surface of water and detected by the receiver. The other three components here, as you see on this side, the first one is called nonlinear fiber Bragg grating. So what we did in this component is allowing the users to create some kind of nonlinearity within the FPG to address some kind of phase control of the input signal. So you can have signals at the input and then create some interaction here, nonlinear interaction, to cause the signal, for example, for switching, you can control to go this path or going to that path. It depends on the design you have. The other component is the tilted fiber grating, which is a component. It's a standalone component, and this component we're gonna demo it later on. You can design the grating and then get the transmission and reflection spectra out of it, and then load it into the FPG component, which we showed you earlier, and use it with the other component in the system. But this is mainly used for sensor applications and for other applications. And the last part here, we're going to talk about it today also, is the pulses polarization meter. And this is, we already have a visualizer called polarization meter. But this pulses polarization meter, it does measure the polarization of pulse by pulse. So I'm gonna show you later on the output of this visualizer, that you can see the state of polarization for every pulse if it is controlled. And this is mainly to address the quantum key distribution applications. Okay, now in this slide here, I just showed you the list of these components added, this location of these components, where it is you can find them in OptiSystem. Like, for example, digital comparator, you go to the default signal processing library, tools, and binary, and so on. So you can see all of those components in the release note. So if you go to the release note typically is found on the documentation folder on the C drive. And you can go through this release note, where you can see, as you see here, the description of the components and where is the location of them, and so on. Next here, as just show you the resources where you can look at the release note, as I mentioned, and then also you can go into the data sheet of the component. Typically, you can access the data sheet of any component through the help button here. So if you click on the help button, you're gonna pop up the data sheet of this component, which also you can access it through the document, the PDF file. It's called OptiSystem component library. So you can search for any component here, and then you find the data sheet of it. So if you go, for example, into here, like, for example, any component, double click on it, and then you go to the help button, and then you have the data sheet, which describes the component and the theory on that component. Now, in terms of visualizers, typically, if you click on visualizers, you see the output of the visualizer. So to be able to access the data sheet, you just put your mouse here, select the component, then go to component properties, and then at that time you have access to the visualizer parameters and settings, as well as the data sheet of the visualizer. Okay. Now, going back again into the presentation. Now, the examples which we're going to look into them is related to the components we added. This example we're going to talk about it is the pulses polarization meter visualizer. Okay, and then if in this part here, let me go into this example. This example, we are talking about only Alice at this moment in this example, just to show you the new visualizer, which is pulses polarization meter component. You have light here, which is this light is switched to control the bases or to control the states randomly. So in this example, I'm using user-defined sequences, where I load these sequences from file, and these files you can we have create them ahead of time. The way you can create random user files, which you can use every time to get the same results, basically. You can go into layout here. I have random pseudo random bit sequence, and I have view visualizer. So if you run this example here, you generate a specific sequence, and then this specific sequence, you can save it as a text file, and this file you can load it to the user-defined component as I did here in this layout. So with this scenario, the purpose of this is just whenever you calculate the project, every time you get the same random sequence, could be any number of bits you generate, and you can get the same results. You can compare it every time. Now, as you can see here in Alice side, you can have control the collinear states and 0 angle or 90 degrees, or circular states on right or left polarization. But here I did the calculation ahead of time. So if you click on the component, just to show you the settings of it, because there is 2 modes of operation of this component. One mode is if you have the binary bit disabled or enabled, okay? So if you do the binary bit is disabled, in that component, you will be able, the pulses which is coming in here into this component, the pulses coming into, let me took another layout here. So this layout here, as you can see, when the component is set as false for the binary port, so you have only single input port, and the pulses which is coming here, you look onto the power level. So you need to set up the level to determine if this bit is 1 or 0, basically in terms of power. So this power here, you can set the pulses power threshold, and then you can tell that this bit is 1 or 0 from the power threshold you set. And then the output of these pulses, as you can see here, for example, in this example here, we have the number of bits. You can look at the number of bits here. We have 32 bits, and every bit here, pulse position, you can look at the power received, the differential of the DOP percentage, the S0 state power, and then S1, S2, S3 states, and then you can know exactly what is the polarization state for every pulse coming to this component. The other part in this visualizer, as I said to you, if you go into the properties and then you click on binary, then you would have 2 input ports, because the decision here on the bit is 1 or 0 is going to be based on a bit 1 or 0 based on binary, okay, not on power levels, okay. And what we have here, we can have a reference where we can compare the states here to do the calculation and the decision on the states, and define the states of the polarization for each pulse. Okay, so this is the 2 modes of operation for this visualizer. The second part we're going to talk about it is the underwater channel line of sight or non-line of sight components. And in this part here, there is a publication. Let me, actually, I'm going to show it later on. I can go over it. There is few publications we had with collaborators to test the components, and it depends on the different applications. So I'm going to show here one example where we have orbital angular momentum example, and you can see here there's 1, 2, 3, 4 modes, and they are combined, and each mode is coupling, getting 50 gigabit per second on each mode, and transmitting them using PAM4 modulation. Okay, so let me go to the next example. We're going to talk about here, also demo it in a few minutes, single photon detector. Now this component here is a very good addition for detecting very low power levels, because usually with band detectors, if the signal power is around -20, -30, depends on the level, you might have a very high errors. Now this components will allow you to receive very low power levels in the range of -80 dBm or so on. Now the components also provide photon counting. We're going to show it to you during the demo of this component. And the last part here we're going to talk about and demo it is the tilted fiber grating component, which will be able to design integrating with tilt and look into vectorial modes and so on. So we're gonna show results for one of the papers we reference in the example library. So if you go to the example library, in example library here in OptiSystem, so if you go into the sensor library, and they're tilted fiber grating, and they have two examples, and these examples, the references are in the example. So if you click on it, you have the reference, and then shows you once you run the example, you can match it with the reference paper on it. Okay, I'm gonna leave that part into the to that demo. Okay, next here, I'm going to talk quickly about the improvement in OptiSystem. I listed here a few of those, and if you need more information, you can get into the release note. The first thing here is the dual port binary sequence visualizer. What we did with it, we add up into it features to do comparison between these sequences at the input ports of the dual port port binary sequence visualizer. So if you go here into the same example in here, this is a dual port time domain, but this is okay. If you go into the component results, and you can actually I have to do it using a binary. So if you go to the component here, visualizers, and go binary, compare, and this component here, if you go into the results, you can see here, this is the addition, the number of ones on port 1, number of zeros on port 1, number of ones on port 2, number of zeros on port 2, and then the number of matched ones and number of matched zeros. So you compare bit by bit on each of these two ports with this component. So this is a new addition to it. And also we did with the single port, we did add to the results. You can look at the results here, and you can look at number of ones and number of zeros on received on this port. So this is some improvement we did. And hopefully this will help in the quantum key distribution analysis. The other part is the digital optical switch in this component here. It used to be only operated with single bit, but now you can have a sequence of bits which operate the switch. So you can have a sequence of bits, and every bit is going to switch the ports to either the first port or second port of the switch. And the other part we added up here is into the free space optical weather condition. This is a standalone component, and in this component you can study the attenuation for different weather conditions. So we added up a new feature here where we have wet snow or dry snow, and this actually, if you go into free space optics here, and then this is the free space weather condition component. So if you look, and this component is standalone, so there is no input, no output. You can run it in a project separately, but what you need to do is you need to check here in the component the weather condition, if it is dry, or it is, for example, there's precipitation, rain or snow, and then if it is snow, you can choose here wet snow and dry snow. This is the new addition we add into the component, and then it can give you the effect on dependent, wavelength dependent, and all of these parameters you can scan and sweep the conditions in the component, and give you the component will provide you with the attenuation. If you go to results here, and you can do data in the report page as well, you can get the attenuation as you can see here, and so on, all this useful information for the simulation. Okay, another improvement in OptiSystem 21 is the update visualizers. It used to have an update, disable and update visualizer. So if you go into OptiSystem, the new version, this is version 21. So if you go here, help, about system, this is version 21. Okay, now if you right-click on the component, you can see here disable visualizers, and disabling visualizer, what we do it typically, if you have lots of visualizer in the calculation, is going to take a lot of resources of memory and slow the calculation. So sometimes it's useful to disable and then enable, and this is the new feature, enable and update at the same time. So when you click, before it used to be 2 clicks. Okay, so this time is 1 click, you can do it, and this is the new addition. So you can disable the visualizers and enable them at the end of after the calculation is being done. This would speed up drastically the calculations. Another addition is the library management. So this part here is you can look at it into the if you go into here, now I need to choose a new file here. You have to be having no components, and then you can here go into tools, and this is library management here. And this library management, it gives you every directory in this here, what are the components in it, and it can, as you can see here, this is the icon, this is the description of that component. So you can go all of these components in each subdirectory, which you can find them in here. Okay, so all of these subdirectories are listed in the library management. Okay. And then here, using the Python and MATLAB Scilab component, in the older versions, you need to put a path for the file, which has the code of the Python code or MATLAB code or what Scilab code. And the new version of 21 is just only put the name of the file. And as long as the file exists in the same directory of the project, then there is no need to put the path of that file. Another improvement here is the toolbar component control icon bar, and this is, if you go into the toolbar here, you can see, let's see, let me close this one, and then if you select a component here, you can have, this is, as you see here, component properties. So if you select the component and then you come to this icon, you can click here and then you get the property. You come here and then you component results, and you come here, you do component scripting, and this one here is the component view. Okay, so if you want to look at the 2D graphs or 3D graphs or the results is all in this icon, you can access it. And this one is component help if you want to look at the data sheet of that component. So you don't need to double click basically here and go to the help. So this what we did in this release is we added up these names so it will be visible to the user. Before in the older versions, these names weren't clear. Okay. Okay, so now what I'm going to do here, we have a small recording for the tilted fiber grating done by my colleague Amin. So I'm going to run this as, okay, so let me see if, okay, to run it. So I'm going to run now.
This is an example of the tilted fiber grating component, which allows you to simulate the reflection and transmission spectra of short and long period tilted fiber gratings. OptiGrating is also able to simulate such spectra. However, this component has a few advantages over OptiGrating. Firstly, this component is able to simulate full vector modes for fibers with an arbitrary number of layers, whereas OptiGrating is limited to 2 layers for full vector mode simulations. Secondly, this component is able to distinguish between perpendicular and parallel polarization when evaluating these spectra, whereas OptiGrating is limited to perpendicular polarization only. Lastly, this component is capable of simulating radiation modes, whereas OptiGrating cannot. Before running the simulation, you'll have to specify a number of parameters relating to the optical fiber, the mode solver, the grating, the coupled mode equations solver, as well as the location of the output files for the transmission and reflection amplitudes. For the optical fiber, the layer indices as well as the layer radii will have to be provided by the user. The user will provide these values as a string. In the case of the layer indices, this will be the indices of the fiber layers from the innermost to the outermost layer specified from left to right and separated by commas. So for example, this leftmost layer here would be the index of the fiber core, then a comma, then the index of the inner cladding, then another comma, and so on. Similarly for the radii, this leftmost value here would be the radius of the fiber core, followed by a comma, followed by the radius of the inner cladding, and so on. These other parameters here mainly relate to the mode solver. Most importantly, you can specify the range of azimuthal orders that the mode solver is meant to solve for, as well as the number of modes per azimuthal order that the mode solver should find. For the grading, there are, of course, all of the parameters of the grading, including the apodization function, which may be either uniform or Gaussian, and in the case of a Gaussian function, you'll also need to specify full width half maximum. For the coupled mode equation solver, you'll need to specify the wavelength range over which you'd like to find the spectra, as well as the number of wavelength points within that range, and the number of modes to include within the simulation, which will affect the accuracy as well as the runtime. And lastly, don't forget to include the location of the text files at which you would like to output the transmission and reflection spectrum. After running the simulation, you can view the results by right-clicking on the component and selecting Component View, and then 2D Graphs. Here you can select which spectra you would like to view, including all mode reflection, which is the magnitude of reflection for all of the modes combined, HE11 reflection, which is the magnitude of reflection of the core mode, and HE11 transmission, which is the magnitude of transmission of the core mode. In this case, I've simulated these results for p-polarized light in a grating. And I've simulated for the same grating the spectra for s-polarized light. And by comparing the results, we can see that there is a shift of about 0.2 nanometers between the s-polarized and p-polarized peaks. This shows that the simulation is sensitive to polarization.
Okay, so now this is a quick demonstration for the tilted fiber grating, and then this example, as I mentioned, it's an example library. You can go there and then check it out. It's going to take a couple of hours to do the calculation. Typically, with these mode solvers, it takes longer time to calculate. Next here is going to be a demo on the single photon detector and how to use this component is done by my colleague Ryan. And here's the...
Hello, everybody. My name is Ryan from Optiwave, and we are happy today to be bringing you a brand new component, a single photon detector. The SPD can be found under the receivers library, and then going under photo detectors. And if we drag and drop this new component allows us to work with low input power levels. This is great for applications in quantum key distribution protocols, non-line of sight underwater channels, or just any application that requires very low receive signal power. You can use this component to be able to do photon counting and time tagging, as well as conversion of light to electrical pulses for further processing and calculation, such as bit error rate. I'd like to briefly show you some of the functionality and great potential that this new component brings to the new release of OptiSystem 21.0. So if you see here under the SPD, we have many tabs that we can look at. In the main tab, we can look at things like quantum efficiency, detector bandwidth, and detector gain. If we go into the next tab, we have detection conditions, which looks at a variety of things. But two of the most important ones I'd like to focus on are the collection time, as well as the photon collection method. These ones will allow you to be able to collect photons for a given amount of time, no matter what the time window is. The other part is looking at the photon collection method, so you'll see that we can choose pulses or CW, depending on whatever our input signal is. So when you're doing your calculations, we can ensure that the counting process is done correctly. Going under the other tabs, we have things like the frequency response, downsampling, random number generation, as well as a noise tab, which is very important for these types of detectors. You'll see that we can incorporate things like the dark counts, thermal noise, and shot noise. And under each one of these, we can have different sorts of calculations of the noise, whether it's defined or calculated for thermal, and different types of distributions for the shot noise. Now that we have an idea of what's happening with the detector itself, we can look into the results. So we've run an example here. If you go under the examples, we can find them in the component sample files, and then receivers libraries, photo detectors, and any one of these can be used for the SBD. Here we're using the continuous wave example. And so you'll see if I go into the results, what we can find are the cumulative or the accumulation of many different amounts of photons. So photon counts, dark counts, total counts, thermal photons, and shot photons, as well as the average photocurrent and the mean and standard deviation of all of the different noises. It also shows you the photon collection method to ensure that you're using the proper collection type for the proper or for the associated input signal. Another way of looking at it is if we look at the component view, we can look at the 2D visualization of this. And if we do this, and I enlarge this, we'll see that we have quite a few different options that we can look at. We can look at total counts, photon counts versus time, the dark counts, as well as photon counts versus time. And so the difference here is that if we click on photon counts per time, you'll see that we can see the statistical nature of how many photons are counted at a given instant, as well as the sort of temporal shape that is associated with a CW laser. So it's constantly counting for CW. I will show just in a few minutes that we have a difference for the pulses case, but if we wanted to sum all these together, we can look these at the cumulative photon counts, and this is what we see here. So indeed, we have an additive nature up to our collection time window, as I was showing earlier. If you also want to take a look at the output, it converts into an electrical signal. And so we can look at the oscilloscope output, and you'll see that it is quite noisy here because we indeed have quite a lot of noise. But you can turn things like that off and look at the output response, and then you can see that it is a nice clean CW signal. Now, if I go to a different example here, one for responsivity, and I run just one of these sweeps, we can take a look at the oscilloscope output, and we see that there's actually a representative version of this pseudo-random bit sequence here. And so this is not only reflected in the oscilloscope, it's also reflected in the photon counts per time. So if I do this again, we look at the photon counts, and indeed we see random amounts of photons being counted associated to the bit sequence. Not only that, you also see that they have a smaller window, which is related to just the zeros and ones. And so it's not a continuous counting, but rather one based on the bit sequence here. So with this, I hope that you have a good overview of what's happening with the component. And I hope that you're excited to use this new component to find lots of very interesting applications. We at Optiwave thank you for choosing Optiwave and OptiSystem, and we hope that you enjoy your new OptiSystem 21.0. Thank you.
Okay, so now for the last demo here in this webinar is I'm going to talk about the underwater channel, and one of the examples which is published recently in the Journal of Optical and Quantum Electronics. This is about underwater optical wireless communication transmission system based on the orbital angular momentum beams. So this is the work which is basically showed you earlier here in this example. So in this example here, as you can see, we have 4 beams. So now you can generate the beams using a single diode or by controlling the LG mode generator. You can generate all the 4 modes at once, or you can generate them using separate lasers. So either way, but eventually what's happened is each of these modes is modulated using a BAM4. As you can see, this component has 2 bits per, each symbol is created by 2 bits. It's a BAM4. And then after that, all these modes, so to be able to generate the orbital angular momentum, which are multiplexed properly, you need to choose the proper LG modes numbers. And in the example, there is different modes here: 00, there is 013, and if I remember, there is 040 and 080 here. And these modes, once you combine them, you can look at the combined modes, as you can see here, the 4 modes together, and then you transmit them over a nonlinear, null line of sight optical underwater channel. We can run them. And in the component here, as you can see, there is many parameters you need to choose from. You can choose the wavelength, you can choose the range, you can choose the salinity of the water, you can choose the type of water body. There is 5 types of water bodies we chose here, and for every type of bodies, we have the constants related to the absorption and scattering. And also you have your custom feature where you can enter your own parameter here. So if you have another types of water bodies, you can address it in this component still. And then in the component also you have different parameters for transmitter to the scope, receiver to the scope, as well as the some effects like scintillation and so on. So this is a very sophisticated model for underwater component. And also you can use the line of sight. The line of sight is a little bit simpler because the light directed from the transmitter to the scope to the receiver to the scope. And then eventually you have a special demultiplexer, and so you can see each mode is demultiplexed separately. And eventually you can do a detection and decision on each mode using the decision circuitry, as you can see here in this part, for example, for this mode. And you have then a decoder, and then after that you compare it with the transmitted bits. So this is kind of a quick demo of underwater transmission. There's a few publication actually on this topic. If you are interested, you just let us know, and then we can pass it to you. Okay, so with this, I conclude the webinar presentation, and then I'm open for any questions. So you can send questions to myself here at my email, or you can send it to support. Thank you very much for listening. So we can go now to the questions. Okay, so there's a few questions here, and let's start. Some of those questions being answered online. So my colleague is answering questions here. Now, in terms of one of the questions, is this OptiSystem can be operated over the Mac operating system? It is not on Mac directly, but they can do. We have some kind of solution. You can operate OptiSystem on a Mac computer through some settings. So if you are interested, just let us send us an email, and then we can provide you with the instructions how to use that. Can you share OptiSystem design project used in the publication? Yeah, you can just please send us an email, and then we can send you the projects. Okay, so why there are 2 modes for operating of the pulses polarization meter? Now, the reason for that is if you wanted to do the decision on that component, on the input of this component, if it is a pulses which is an optical signal, it's different than when you want to do analysis on a signal coming from a binary signal. So because in OptiSystem, there's 3 different types of signals. There is electrical, optical, and 4 actually, binary and M-ary. So it depends on the type of the signal coming. You need to know how to analyze it. And we have option to do the analysis on an optical pulses, which carries signals, and this signal can be higher. The power level can be different. So we don't know if this bit is 1 or 0. So we have added up the threshold to decide on 1s and 0s. And then the other option is if it is binary coming directly into the component. And that scenario, we have to enable the binary. the binary option. Okay. So do you think that OptiSystem 21 is able to model space division multiplexing? Is actually, yeah, there is a few examples on how to do spatial division multiplexing and OptiSystem. So also, if you need any help, just send us an email and then we can help you on that. How to design underwater free space optic channel. The example which I showed you is an example designed in OptiSystem for underwater channel. The best scenario to do is you can take one of the examples also using the free space optical channel in air, and then you can replace it in water, and then you start to play around with the laser wavelength, with the range, and all of this, because the operating wavelength and the range are completely different in terms of between the transmission in air or transmission underwater. Another question here is, what are the main parameters that need to be adjustable for underwater communication? So the most important part is the type of water, and based on the type of water, you determine the absorption and scattering of the light inside. And then the other part is it direct beam or it's indirect beam. This is the second part. And then proper choice of the wavelength of the lasers. Typically, you use around 530 nanometers or so. Now, the salinity of water is also there. There is other calculation for the effect of temperature of the water and the calculation, especially in the nonlinear, null line of sight channel. You can have this addition of the calculation. So question here, can we use SPD single photon detector to detect high power signals? The SPD can be used for both very low power signal and high power signal, but you can, if you have high power signal, you can use the bend detector, which is well suited for that. Another question here, how to use OptiSystem for Internet of Things real-time application. Okay, so one thing which is when we created Opti instrument software is to allow users to communicate with equipment at the same time use the data into OptiSystem. So what we are working on it right now on a new graphic control where we will be able to get live data. And hopefully in the next few months, we will be able to demonstrate that. So something is not clear yet on our map, but this is something we are contemplating to do very soon. Can we develop a phase OTDR setup for vibration sensing by assembling all the components in OptiSystem, such as Maxenter, instead of using the PHY OTDR components? If yes, what are the limitations? Okay, so this is the problem with the PHY OTDR is the back reflected relay scattering signal, and then at this moment is the relay scattering in the optical fiber component. They are parameterized and not time dependent. So that's where is the limitation. That's why we created this PHY OTDR component. However, we are working also in introducing a new component would address that. And we are working with our collaborators at different universities to address that. So this is hopefully can be addressed in the near future. Is it possible to use non-line of sight underwater communication system with cloud licensing? Yeah, so sure, it's can be used with cloud license or with the perpetual licenses. Either one can be used. Can I use the software for PhD research? I mean, this is the OptiSystem software. The beauty of it is you can use it for industry application and for research applications. So there is lots of publications in the field using OptiSystem. So in the different applications. So I think it's a very useful software for doing research. Can we design a mirror array on OptiSystem? Mirror, we have a device called bidirectional reflector, and then you can make this device as a mirror by controlling the pass through light. So you can make 100% reflectivity and becomes a mirror, or depends on the application. Again, you can let some light go through. How to design real-time project of FSO system using OptiSystem software. Like, I mean, there is few examples in OptiSystem about using the free space optical channel in a design, but it depends on your envision of your setup. In principle, setting up an example in OptiSystem should be straightforward. Is going to the component library and drag the relative components into the layout and then connect them. The issue is if you are not sure about the location of one of these components, what you need to do is you can use the search. So the search is done this way. I can show you quickly. If you put your mouse in the gray area here and do right-click, you can say find component, and then you can enter the name of the component, and let's say, for example, polarization controller, and then all the components which has the words polarization or controller would be displayed here. You can refine the search, all word search or single word search. And if you go to any component, double click on it, it takes you right away into that component. Okay, so this is a way to go quickly into the components. As I mentioned, there is 580 components ready to go for usage in OptiSystem. However, with the co-simulation with other software like Python and MATLAB, you can write your own code in these languages and then incorporate that design into OptiSystem. So you can have a wider range of applications with this kind of system. How can we use OptiSystem to establish a UAV FSO communication link? So this is something we are working on it right now. And we are hoping to add it up in the near future. So this is something, again, we don't have a component right now, but this is something is coming up hopefully soon. Can we demonstrate how can important Python code? Can you demonstrate how we can import Python code? Okay, so just quickly here, just to show you, if you go into the example library, file examples, and in the example here, there is Python directory. And in the Python directory here, you can see there is different examples and the SDK to create your own Pythons and so on. But if you go to the examples into Python components directory, you have 4 examples on that. And in one of these examples, as you can mention, clock recovery, memory threshold, and so on. So if you choose one of those, you can see we created the example using the regular component of clock recovery and a component using a Python code for that clock recovery. And now in the component here, what you need to do is you need to load the Python file. And the Python file, you can see it here. You can have your own Python file. You have to make sure that you have proper initial coding at the end of the coding to enable the transfer of the signal. That's the most important part in usage the software, is how to take the signal from the input to the output. Okay, so the input, you need to read the signal from OptiSystem, and the output, you need to pass the signal into the other component. That's the key part in any co-simulation between OptiSystem and MATLAB or Python and so on. Another thing here, do we use solar cell in our optical system, or do we need to integrate other applications? Okay, so in OptiSystem currently you have a component where it is under if you go into the source transmitter light sources, optical sources, here we have components called spectral light source. And there is an example in OptiSystem we show that we load the spectral characteristics of the sunlight. Now we are adding a new component actually right now. It's called photonic power converter chip, and this would allow detecting high power lasers and create electricity to power up electronics eventually. And this is, we have two parts in this project actually, is experimental data as well as measured data, as simulation to do this component. So this is something coming up in the next release. We are finalizing it in the moment. Okay, so we have 1 more minute for the hour, but I'm going to take one question. The remaining questions, what we're going to do, we're going to answer them separately and then send them to the person who asked them. Also, we're going to send the recording to all people registered of this presentation. If you want the presentation, let me know so we can pass it to you. Okay. Can we design a hybrid Wi-Fi RF system and OptiSystem? Okay, so we don't have Wi-Fi component. However, as I mentioned, you can create the component in the MATLAB or Python and then add it up into the system. RF system, definitely we have all the components hopefully necessary for this for RF and designs. And that's it. I think it's for the time being. I'm gonna stop. Thank you for everyone attending the webinar. And as I mentioned, if you need a certificate or you need a presentation, just send us an email. We'll send the recording to everyone attended. Thank you very much. Have a good day and night. Depends.